Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to summarize everything we learned in this section, which was focused on Deep Q learning. The surprising thing about Deep Q learning is that we didn't really do anything new. All of the techniques we used we had developed previously. The only changes we made were hyperparameter changes and things that seemed surprisingly simple. So to recap, we actually already covered Q-learning in our previous reinforcement learning course, so you're familiar with the basic form. We take the TD0 error and do gradient descent with it. We did this both with Q-tables and in this course with approximation methods. Of course, deep learning is also an approximation method, but as you may have noticed, just trying to plug and play any old neural network won't result in convergence to a good solution. We were, however, able to use a type of neural network called the RBF network that has a fixed feature representation. So that's everything we did up to this section. In this section, we answered the question, what additional tuning can we do to get neural networks to work with reinforcement learning algorithms like Q-learning? So let's list out some of those techniques. There's experience replay. This should remind you of batch gradient descent, where instead of stochastic gradient descent, where we just look at one sample at a time, we look at a bunch of samples that we collected from the past. It's important to note that we always sample from the most recent set of experiences. The reason we want to do this is because when we use the TD error, we're not doing true gradient descent. We're only doing an approximation of gradient descent. And that's because our target is not a true target, but rather it's yet another prediction made by our very own model. And that brings us to the next technique, where we use a separate target network that periodically copies the weights from the main network. Another modification we made was for how to model Q. Instead of doing a feature expansion on the state-action pair, as in traditional reinforcement learning, we instead do a feature expansion on just the state and have an output node for each action. In terms of neural networks, you can think of this as each of the inner layers of the neural network finding a good feature representation, and then the final output layer being a separate linear regression for each action. Something to consider though is, how would this work if you had an infinite number of actions? Finally, we saw some techniques that allow us to apply deep Q learning to video games. Specifically, we don't just want to extract features from the video game manually. Since this is deep learning, we would like the neural network to learn feature representations of the input using gradient descent. And so, as you know, our main tool for dealing with images, which can be considered the most raw feature you can get from a video game, is the convolutional neural network. We also looked at this idea that we don't have to consider the state as just information from the current time. We can also incorporate any other information into the state that we would like, for instance, images from previous frames. So this is exactly what we did. Our reasoning for this was because we can't infer motion or velocity from a still frame. And of course, motion is very important in a video game because it allows us to predict what's going to happen next. This is just like trying to catch a baseball. You can look at the trajectory of the baseball, and your brain will be able to predict where it's going to land. So with these simple techniques, we were able to combine deep learning with reinforcement learning, but not only that, we were able to scale it up to much more complex games like Breakout. And of course, as the original authors have shown, these same techniques apply equally well to a number of other Atari games, like Pong, Space Invaders, Sequest, and Beam Rider.